Okay, so let's begin the class today, all right? As I mentioned earlier before I hit the recording button, this material will not be on the exam, but my cat is actually on this table. Oh my God. Sorry, guys. She was trying to sabotage the lecture. Uh, Okay, I think now that I have sorted out the problem with my cat trying to hit the keyboard button randomly, again, the things we are gonna cover today will not be on exam. All right, I'm gonna talk about what are the other tools that are getting popular these days that you can use to run things in parallel, right? What are other new things? Anyone want to mention what are the new languages that you have seen so far? Anyone heard of this thing? It's called Go, actually. It's from Google. So Golang is, I would say it's another alternative to Rust, right? Uh, and to be honest, I have to say that this is simpler. It's more geared toward, okay, can we learn a language really quickly and develop code that are relatively fast, right? It's simpler than Rust. It's a I would say it's a go-to language, and no pun intended, if you want to develop parallel programming really quickly, right? It doesn't mean that it's gonna be super fast, right? I still have my gut feeling is like if you optimize the code on Rust quite a bit, it can be faster. So that's why I say it's likely to perform worse than Rust, but still provide you memory safety, which is one of the most annoying thing when you have to develop parallel program. And that's why Golang is actually enabling you to develop parallel programming quickly, right? So let's go a little bit into that, this thing, right? The first thing that you might come across when you try to learn Go language, which we're not gonna cover that in detail in this class, but you're gonna go through something called the Go routine, right? Basically, this is your method, right? Basically, your method, the function call, right? For Go to generate parallel execution. And when you use the keyword Go, there's so many word Go here. When you use invoke the keyword, right? It actually invoke a function in Go routine. And this function would execute concurrently with other tasks. And here are some example, right? So I definitely would recommend this particular website. It's called Go by Example. And in there's a link for Go routine. But Go by Example is a great resource for you to learn, right? For you to learn how to use Go language. If you want to work in a database system, if you want to deal with new database management system, or have to like think about, okay, I might have to modify the code over there a little bit, consider Go, because at a lot of new still in research kind of database using Go. Surprise. The reason behind it is it's easier to develop and it's fast, right? And here are some of the example. Well, you can take a look at this. The import, the keyword import is basically what are the library that we want to import. FMT has to do with I/O so that we can use printing, right? We import the ability to kind of like measure time and deal with time, such as I'm gonna run something and stop, or run something and sleep. Sleep mode basically means that I pause, which I can resume later. Then I call the function here called f, right? Function f. I take in string as an input. I loop between 0 and 3. You might see the same similar syntax in almost modern languages, actually. You just need to make sure the syntax is correct when you actually run it. You can say fmt.println, as the fmt is used for I/O, so they can print, right? So you can print this value, right? And then you can say, hey, put the word direct, right? Direct into function f. And then you invoke, as you can see here, go, right? F, go routine, and go function message string, right? When you look at this, right? When you say F direct, it call the function, but without the go routine. But when you invoke this, right? Go, it now invoke coroutine, go routine, which will enable parallel execution. Definitely, if you are curious, try the go by example and try out examples over there. That's how you can, I guess, quickly learn the Go languages. If you have any questions, feel free to let me know, because for the majority of the rest of the class, I'm gonna talk about the GPU. Hopefully you are interested. I'm kind of feeding this topic to you, but I feel like this is one of the topic that gets more and more important. Running your program on non-traditional CPU architecture is going to be one of the things that came up in the future, right? So GPU in modern system, what do we use GPU for? Let's say I buy a GPU, RTX 2080 Ti, which is a little bit older, but hopefully the price go down a little bit compared to the 3080. We use it for gaming, right? And I can buy them. I can buy these games, which in fact I bought it. I play them all, right? Um, so it's fun, right? You buy GPU to render graphics, right? What will happen if I run these games without a GPU? You're gonna get really low frame per second, right? Frame per second, it means basically within 1 second, how many picture can your computer generate for your eyes to see on the monitor? Right? You look at the monitor and you will see a lot of picture get refreshed typically is if it's 60 frames per second, so it means there will be 60 images within 1 second. So what will happen if I play a game that is low frame per second? Anyone has a chance to, well, obviously it's not fun. Anyone has a chance to actually throw up when you look at like, or when you play first person shooting game and frame per second is not sync. If you haven't run into that yet, trust me, I was in your shoe. 10 years later, I can't play those games anymore because I'm gonna throw up. The problem is your eyes require some form of synchronization. I want and I expect I'll see the next image within 160 of a second, but somehow your monitor show the image and then another image later, another image way later, and then another image not as much later. So you don't see the same interval. When you don't see the image at the same interval, your eyes is basically have to process those weird pattern of the image showing up, and it actually can make you like nauseous, basically. Right. So basically, it is not fun if you don't have the GPU. What about in modern system, right? Around year, I think 2012, right? NVIDIA came up with this concept called CUDA. Anyone here have seen the NVIDIA ads and things that they can do at all besides gaming? So essentially, right, you can use the GPU to run many other applications. We call this general purpose application on graphic processing unit. What does it really mean? We let the GPU run any application we want to program. And literally, we can do that. We can actually run things on a GPU. What are these things? Outside of gaming, what do you hear about people using the GPU for? Mining, ML, rendering, right? These are all legit example, right? So hopefully by the end of this class, if you want to use your GPU for cryptocurrency mining, well, without any respect to the environment, because it's actually a much like super waste of energy, and it actually it's actually really bad for global warming in for many of these crypto algorithm. It's not energy efficient at all. But let's say after this class you want to do that, you can, right? And hopefully things you learn in this class would enabling you to think about, how do I write my program such that it's faster on the GPU, right? So you can do machine learning. You can rendering. Like rendering the video is actually similar to a traditional way to use the GPU, which is generating the image for well, in this case for a video file, right? It's not for the monitor anymore. And in modern system these days, it's actually available. You can buy if you have a lot of money, right? Well, yes. So if you want to go there, my argument is right now a lot of the common cryptocurrency still doesn't use the algorithm that are energy efficient. I'm talking about the algorithm. So even though they use renewable energy, it's still a waste of energy, right? It's a waste of energy. I have heard Ethereum is going toward a better algorithm that's basically more energy efficient. So I hope in the future they kind of change the way they first of all synchronize and do the handshake of whether the transaction is legit or not. These can be made more energy efficient. At the moment they're not, basically. At the moment they're not, but it can be made more energy efficient. Uh, so it's a totally orthogonal problem with like whether you use renewable energy or not. That's like a two different huge problem, right? I see benefit of using what's it blockchain, but the technology have to evolve a little bit more. It is not ready yet, I think, for a lot of a lot of things that require for energy efficiency and performance, right? But I see benefit. I mean, definitely there's a lot of benefit in the technology itself, right? It's just a matter of how do you implement so that it's much better performance and much better energy efficiency. So outside of this, you can also have a GPU in the cloud, right? And because of the massive parallelism, right? Any keyword that you've seen before, these keywords will come back and haunt your, I guess, career as an engineer, right? You are going to write program or come up with algorithm that is parallelizable to make it fast. And if you can do that, you can then take advantage of the GPU. A lot of mining algorithm actually has a lot of parallelism. That's why it's really good to run on the GPU. So what does the GPU fundamentally look, right? So in this slide, again, I'm gonna talk about two keywords that I don't think you ever heard before. Feel free to look it up or check back with me after this class. But what they do fundamentally is they employ two things. The first thing is single instruction multiple data, or SIMD. SIMD is basically, anyone hear about assembly? Anyone here heard about the term assembly before? So the difference between assembly inside a CPU and inside the GPU is how many operations is done per one assembly instruction in CPU. So let's say I see an add instruction, right? How many operations are you doing to how many pieces of data? So let's say I wanted to add A plus B into C, right? You do one operation. I add A and B, and then I store results into C, right? This is normal in CPU world. In GPU, what you can do is, well, you still use one instruction, but when you add, you're gonna add basically array of data. a vector of data together. So one instruction will now operate on 32, 64 operations. Basically, one instruction turns into 32 or 64 add operations or multiply operation on 32 or 64 different pieces of data. So what's the benefit of that? Having one instruction operate on 32 times more operations. What's the benefit of that? Faster, right? So the key benefit is if you have a lot of parallelisms and if somehow your program has to do those 32 parallel add anyway, it's done in one instruction. A lot better throughput, right? A lot better throughput. Another concept is called fine-grained multi-threading, which we were definitely not gonna talk about it in this class too much, right? But this is to make the GPU even faster. Is to make the GPU even faster. But as I said, they come with requirements. Your algorithm has to be, I would actually stress on this word, embarrassingly parallel. So any samples of the operations you've seen so far that are really, really parallel is map. Is the map operation embarrassingly parallel? By embarrassingly parallel, I just mean that it has really high parallelism. So is the map operation really has a really high parallelism? Well, the answer is yes, right? Because if I have a vector of 1,000 elements and I apply a map, how many I can do in parallel at any given time? I have, yes, 1,000 elements, right? So you can do all map in parallel, right? Because there's no dependency, right? So basically, at the end of the day, I can apply them all in parallel, assuming that I have a hardware to do it. The GPU is that hardware designed to handle this particular case. Your program also has to be embarrassingly similar because of single instruction multiple data. I have 32 adder, but I have to make sure the 32 operations are the same. Add, multiply, right? So your program should have a lot of repeated operation. Again, that's why machine learning and crypto mining are really, really good to run on a GPU because first of all, they are embarrassingly parallel. Second of all, they have a lot of repeated operation. All right. Any questions so far? Anything you're curious about and you want to ask me? If you have any questions, feel free to leave it on the chat. I'm gonna come back whenever I see the new questions. All right. So then, you understand conceptually what are the GPU. I'm gonna talk a little bit more about how does the GPU core look like, right? So let's say you have a program, CUDA or OpenCL program that basically can be run on a GPU, right? When you run it, what happened? So when you run it, these CUDA program will get the way you program that, you are going to generate thousands and thousands of threads that do the same thing. Add. Do this for loop, for loop, for loop, for loop, for loop. But for each iteration, for loop for I equals 0, for loop for I equals 1, for loop for I equals 2, for loop for I equals 3, right? The parallel for loop would be broken down into multiple threads, and we call this a thread block, right? And then each of this block will also broken down into another subunit called a warp, right? And the GPU itself, and then basically your program will consist of multiple thread blocks, multiple warps. The GPU, or whatever they call simultaneous multiprocessor, these are the GPU core. These are the GPU core. The GPU core has the execution unit or the ALU, which is just basically adders and multiplier. Adders and multiplier. But there are tons of them, right? In these modern day GPU, you're gonna have 32 or 64 adders, 32 or 64 multipliers, so they can do 32 or 64 add and multiply at the same time, which is nice, right? This is called execution units. In NVIDIA terminology, they somehow call this CUDA core, which, to be honest, it's a really, really, really bullshit way to call this thing. It's not a core, it's just one execution unit, all right? The core itself consists of multiple execution units. A thread block would get dispatched, right? There's so many, I know it LOL, right? But there's so many things that NVIDIA do that's a really, really PR thing that I don't totally agree with, but I can see why they do it. It makes the illusion of GPU has so many core. It has 3,000 cores. How is that possible? Well, they call their execution unit one single adder, one core. Well, it is not as simple as that. Actually, the execution unit, one execution unit consists of adder and multiplier, things like floating point, adder, multiplier, and those as well. But it's not a full-blown core. It's not analogous to a CPU core at all. So this thread block would get distributed across multiple GPU core or SM. When you buy a GPU, those typically comes with 15 or 30 SM. Your GPU that you buy nowadays would have a lot of GPU core. You also have a lot of execution units or CUDA core, right? The thread block would get dispatched for each of these core. And the way things run is a warp, as I said earlier, there's one warp will get dispatched to the execution unit and say, hey, do that add. But in one cycle, if I have 8 execution units in one cycle, how many adds I can do? So my question is, if I have 8 execution units, so within one cycle, how many adding I can do at once? 8, right? So you can do 8. So let's say, what if I have 32 execution units in one cycle? How many I can do at once? So let's say warp size is 32, right? And what if my GPU has 30 SM? How many adding I can do at once? For the entire GPU? Yes. 32 multiplied by 30. That's actually 950, 60 add, right? In one cycle. In the CPU world, how many add I can do? In the CPU, probably less than 20, right? Yeah. If you have a huge CPU with like 32 core, maybe you can do around 64. Actually, you can do multiple per cycle. It has actually multiple adders, but it's not as many, right? Okay, so question, do you see the benefit? Why some GPU application is really, really fast, right? So in one cycle, even though the GPU is clocked at the speed as half of the CPU, and this is normal. Like if you buy a GPU, it would be clocked at around 2 gigahertz. In the CPUs can be clocked at 4 gigahertz these days. So maybe the clock cycle is about half, but you can now do the thousands of those at a time, right? So this is awesome. This is the great thing about the GPU. And then you dispatch your thread block everywhere, right? And as I said, CUDA core, when you see the GPU spec sheet, CUDA core is one execution unit. It's not an actual GPU core, right? I always call this like a PR stunt, which I don't like too much, but I can see the reason why again, because it actually does compute operation, right? So I'm going to talk about something that we would Oh, what's that tensor core? That's a really great question. Anyone here heard about tensor processing unit or the TPU or the tensor core? Anyone hear about this before? So the Google Tensor Processing Unit, the one that Google have, is essentially another piece of hardware that's designed to do tensor processing. Tensor processing is what TensorFlow and many operation in machine learning is using, which most of the time can be broken down to things like matrix multiply, add, gather operation, scatter operation, things like parallel multiplying and adding. Right? So those are special hardware. Put it on your computer just to do matrix multiply. Well, it's not as simple as that, but most of the time it's designed to have a really high throughput for the matrix multiply operations. That's actually that's everywhere in machine learning algorithm. So it's another piece of hardware. Right? So here's so hopefully that clears things up, right? When you see Tensor Core, for the GPU, I actually need to double check whether they use the typical GPU core to serve tensor operation. Because you can do matrix multiply really fast on a GPU by default, right? So I'm not sure if they need their own tensor core. But the Google TPU, Tensor Processing Unit, is basically its own ASIC. ASIC is basically special hardware. Whenever someone said ASIC or ASIC, that essentially means that I design my own hardware. I don't rely on CPU. These are the things that I just design to run certain operation really fast, right? So let me go to like a basic internal of the CPU. This is like how the CPU look. And I'm not gonna go too much of this because I just want to lay out things like this is where you do an add and multiply. You have the main memory right here. You have the decoder which try to figure out this instruction is an add instruction, this instruction is a multiply instruction. Basically convert the ones and zero into instruction that the computer knows. This is the unit to actually get the next line of code, right? To get, hey, you are at this assembly code, this line. So go next to the next line in the next instruction, then go next over here. A 5-stage pipeline. So if you enroll in the ComsysArc class, this is basically what we covered last week. In CPU world, we break the operations into stages. So you can fetch, decode, execute, handle the memory, and then commit everything back to the register file so the programmer can see the changes. Basically, the goal here is to make CPU faster. In what way? To make instruction processing per instruction really fast. So the high-level overview of the CPU is this. You are going to have a lot of cache. Things like a cache for the instruction. Oh, so there's a question, or does this have to be this specific layout? Is this for the CPU design or is this for the GPU figure I showed earlier? Just to make sure I am clear on the question. Oh, you can move things around. So let me go back to this slide. Any lines I draw here is just wiring. So it doesn't have to be the specific layout. The thing about hardware is as long as it operates, it's fine. So you can design your own thing. Right, this is what I draw so that it actually makes sure it fits within this PowerPoint slide. So in the CPU world, there are many things that are being added to make the CPU fast, right? Anyone here heard about the word cache? So a cache is basically, think of a cache as a small memory that are really fast. The memory that you buy, DRAM that you buy, right? The one that you buy and plug onto your motherboard, it takes about between like 12 to 60 nanosecond. These days might be 40 nanosecond to access. the cache would take about 1 to 2 nanoseconds. It's a lot faster than going to the main memory. So the CPU put in a lot of this cache everywhere. If you need to go get your next line of assembly code, have the cache for that so you can get the next instruction right away. You have a decoder, right? You have a relatively sized ALU. You can do add, multiply, and some complex operation. You have the load store unit. You have the write back phase that actually commits. Basically, when you're done with one instruction, write the result back so the programmer can see the changes. So these are the basics, right? Then in the CPU world, there's this thing called branch predictor logic. What does branch predictor logic do? Anyone want to take a guess what this particular thing do? Anyone hear about code branch? So it predicts what the program will do. Specifically, how many people use if else before? If else, right? Everyone use if else. And the thing is, have you imagined, because basically your program is a bunch of memory, right? It's a bunch of memory locations. If you have an if else, one of them will be the next line, right? In assembly code, it will be the next line. Let's say the if is in the next line. Where do you put the else part of your code? Somewhere else. Okay. Basically, it's another place. Your code literally branch out. If it's true, go here. If it's false, goes here, right? So a CPU, what does branch predictor logic would do to the if else? Yes, exactly. It actually predicts, are you going to the if or are you going to the else? There's a reason behind that, and the reason for that is for performance. It actually makes your program faster. I'm not gonna go deeper into that, but basically this is the logic that predicts, are you going to the if or are you going to the else? If you have a loop, are you staying in the loop or are you exiting the loop, right? So it's there to make your program faster. Instruction scheduling logic and reservation station and future files. Remember our data flow lecture from lecture 1, data flow diagram, data flow paradigm. What is the benefit of data flow? Versus one Neumann, which is run line by line. You execute as soon as data is available, right? So what's the benefit of that? What's the overall benefit? It improves performance, right? It makes things faster. I have my data, I'm gonna run it right away. Why wait? Right? It doesn't have to be the order of the code that you write, right? So think about it. You write code in C. Let's say you write code in C language. Is that a data flow paradigm or is that von Neumann? In C or in Python or in Java? Is that data flow or is it von Neumann? It's von Neumann, right? It's actually von Neumann because you go line by line by line by line. Whenever your program go by first line and second line and third line and fourth line, that's von Neumann. But I said data flow is faster, right? Data flow is faster because when data is available for your function, you execute the function right away. Right? Yep. It's okay to get things fixed up, but the key here is most programming languages is von Neumann. CPU internally in the hardware, these two things convert that to data flow. It actually convert your program to data flow program automatically. So you didn't even realize your C code that you're running. When you run, the hardware convert this to data flow problem. All right. So basically, there's a lot of hardware design to make sure this happens, to make sure this is fast. Right? Are you with me so far? Okay. And then you have a lot of SRAM cache in the memory. This is, if you are in the system skill, I'm gonna preach over, write the program so that it actually fit within the cache. It will make your program fast, right? So you have a lot of cache, a few megabytes of cache to make sure you don't have to go to the memory all the time. This one last thing is also for the to make sure you can do data flow program without programmer realizing that they are running the instruction way ahead of this line. Right? To make sure a programmer see the same von Neumann model. So many things are being added. So the conclusion here, my key takeaway is the many other things here are added to improve single thread performance. Can you give me a second, by the way? My wife is calling. I want to make sure these things are okay. I'll be right back. Resume this. Okay, so many things on the CPU are being added to improve single thread performance, basically to make the program go as fast as possible if they're single threaded or a few, like basically a program with a few threads, right? How about the GPU? The way you design the GPU is this. So let me start from this. I'm gonna look at the CPU design and I'll take something out. I'm gonna take the branch predictor out. I'm gonna take the future files and instruction scheduling out because I don't need that. I'm gonna make it simple. Von Neumann, fine, I'll use von Neumann. What the GPU change is, with the ALU, I'm gonna have tons and tons of adder. Right? With me so far, basically I take things that I feel like I don't need out. I'm gonna add stuff that I feel like, okay, I'm gonna need this. I'm gonna need a lot of adder, a lot of multiplier. Right? I have to support thousands and thousands of threads running at the same time. So I'm gonna have to add more register. I need to make sure I can store these things. I'm gonna take the SRAM cache out to make it software managed. So if you program in a GPU, you can manage the cache. You can manage the cache on your own in the code. Right? What else? That's kind of the gist of it, right? Many of the things are added here. Instead of having a fast single-threaded program, the things that are being added here is added to improve what we call instruction throughput. What is a throughput? So let me ask this. What does throughput mean? It's how many things you can process per unit of time, right? Throughput is basically things you can do per unit of time. Instruction throughput is basically how many instructions you can run per a unit of time. So in the GPU world, you want to do as many add, many multiply as possible per a unit of time. Why is that good? Parallelism, right? So your program is faster. So let me mention, okay, what happened when I execute an instruction in the CPU? In one CPU. Let's assume this is one CPU. One instruction at a time, one operation at a time per CPU core, right? You have this fancy, what we call out of order. This is the data flow thing that I mentioned earlier. Is a CPU imitation of the data flow model to make your program fast. So you have this fancy out of order execution logic to make sure your program is fast. You have fancy speculation such as the branch predictor, right? You can predict the address of your load and things like that as well. You are going to speculate a lot, predict a lot, so that you don't have to stop running, right? You have fancy branch prediction, predict the outcome of your if else, right? So it's fast to finish one instruction in the end. If you want to finish one instruction, it's really fast. On a GPU, when you run an instruction, again, one instruction at a time, one warp at a time, how many operations. How many operations are in a warp? It can be 32, 64, 128, right? A lot, right? A lot of operations. So in one cycle, you're gonna do a lot of operations. The word lane I use here is basically that execution unit. We call it lane because it kind of makes sense. Like you go feed your thread in a lane. And its own lane would have its own register files to handle that thread. Basically, each lane is one thread. There'll be hardware to process all these threads. The benefit is really high throughput. Many operation can be done in one cycle. I wouldn't have a question, right? Okay, what if I instruction take more than one cycle? What do we do? This is where fine-grained multi-threading comes in. So I'm gonna have a picture of the GPU core. Right? With me so far, basically a GPU core would have a thread block, as I said earlier. A thread block would have multiple warps. Each of these blocks is one thread. A collection of thread is one warp. A collection of warp is a thread block. That's all. A box here is a thread. A bunch of threads grouped together is a warp. A bunch of warp grouped together is a thread block. All right. The way GPU run things is each cycle, right? A GPU core would pick one of these warp. Let's say in this cycle, it say, hey, warp D, run. It run in lockstep. It run in lockstep. What does running in lockstep mean? Any one of you seen the way soldier march, like in a march thing where they would like come in group and walk together, right? Walk together in lockstep. The same thing here. Every thread here would run the same thing, exact same thing. Add. Branch. Add. Multiply. Subtract. Right? It's all do the same thing. One warp at a time. The next cycle, because warp D is still adding. Let's say it's still adding. It's like, oh, I'm gonna add. I'm gonna wait a while, maybe a few cycles, like 3 cycle, 4 cycle. In the meantime, what would be the thing that makes sense for you to do? Warp D is still processing the add. What would the GPU do? I have warp A, B, and C left. So what would you do? So while you're waiting for the add, right, you then switch to warp C, for example, right, in the next cycle. And in the next cycle, I'm gonna do warp B. In the next cycle, I'm gonna do warp A. Right? So you see the picture now. Every single cycle, I'm gonna do something useful, right? Basically, every single cycle, the GPU would pick, oh, okay, this warp is still processing. I'm gonna process the next one, right? So this is how you can get even faster, right? Because every single cycle, I'm doing something useful. So let's say warp A run into a memory load. I need to go to DRAM. In GPU, going to DRAM takes, by my measurement, hundreds and hundreds of cycles. So it takes a long time, right? So let's say I have 8 threads here per warp. It means I'm loading 8 different pieces of data. Right? I'm loading 8 different pieces of data. This will take a long time. In the meantime, GPU is still active. It's still basically run. Okay, fine. Warp A is loading. I'm gonna wait for them. Warp D, let's say Warp D and C and B are all done. So I'm gonna switch over and do this rotation between B, C, and D. It never stops, right? So the GPU is active. It's doing something useful. So do you see the benefit of doing this now? Doing switching between warps. This is called fine-grained multi-threading that I said earlier. That's why the GPU core is essentially single instruction multiple data plus fine-grained multi-threading. What we do here is called fine-grained multi-threading. And I don't even have to waste the cycle on a GPU. It's always doing something useful, right? Not until all of them is like loading. So that's the only case when GPU core actually stops. Yeah, fine, I'm gonna wait for the data. I can't run anything else, right? So over here in this case, you can't run anything else. So we're gonna wait until some of the data come back. That's when you become active again, right? So do you see the benefit of running things on a GPU now? What are the trade-offs, right? So the good side is obviously your program, if they contain multiple similar instructions, is gonna be super fast, right? The number of instruction per cycle is core multiplied by the number of lanes. Number of lanes is number of execution units. But it's gonna be slow for each of the thread, right? For each of the threads, they're gonna be slower. You don't have these fancy things to make them fast, right? So we are going to go on the bad side of things. This is some of the stuff that I want at least the younger generation of engineer and science, like computer scientists, to understand. GPU is not perfect. The reason behind I need to show this slide is actually this. So let me pause. The trade-off, right? So here's the trade-off for the bad side of GPU. Right? And based on the discussion here on the chat, I think it's clear. First of all, if you're running a single thread thing, like for example, if you want to use the GPU to run an OS, probably not going to be that much faster, right? It's going to have really bad, horrible, actually, single thread performance. So if your program is not parallelizable and you want to run it on a GPU, good luck, right? It's not going to be fast. It's not going to be fast at all. Because you don't have any hardware designed to make a single thread fast. The GPU is just not designed that way. Your program performance on the GPU would depend on the application's parallelism. If you can run many things in parallel, it's gonna be awesome. Your life is good. It's gonna be extremely fast. Otherwise, if your code has, say, for example, a lot of critical section, a lot of synchronization, it's single thread, it's even multi-threaded, but it has a lot of synchronization, it's going to be slower, right? So let's go through some example. What are the things that make the GPU slower? So let's look at if else. I don't know why there's a red. Is there a red box showing on your screen? Okay, should be gone. So let's say I look at this code, right? I say if a equals 0, do something else, do something else, right? And let's say this is my warp. What happened in a GPU? So do I have to run them all together? Because I just said I have to run the exact same instruction, right? So anyone imagine what do I do here? If first 3 of them are true and 5 of them are false, what do I do with this if else in a GPU? Anyone want to take a guess? Okay, first of all, you see the problem, right? What is the problem? Can someone explain what problem do you see here? I'm gonna give you 2 minutes. I'm gonna get some more water, right? I'll be right back, but well, exactly. And then you got a problem, so I'm gonna get water later. It's not the exact same instruction, right? The the true part here are going to run whatever is in the if. The rest would run whatever is in the else. One of them run do something, the other one do something else. So what should I do? GPU is designed, you must run the same instruction. So what do we do here? What do we do? Exactly, you're right. We run whatever is true first. Yay! Right? And then once that's done, what do we do next? When I have the dash line, it means I do nothing. I just say, hey, no operation, don't do anything. Then run run whatever is in the else, right? So let's say this has 3 instruction. This has another 3 instruction, right? And you have 8 threads per warp. if I can do the whole 6 instruction together in the maximum case, I can even get to basically 8 multiplied by 6, right? This is total possible instruction per cycle. Total number of instruction you can run, basically. Is 48 different add, 48 different multiply. In this example, how many do you actually get to do with this particular example? You can do three threads per 3 instruction here, and then 5 for the 3 instruction here, right? So how much is that in total? 24, right? So you only get 24 out of 48. So what's the slowdown here? How much slower do you get? Half. Yes, you barely get half the performance, right? Just because you have if else. So you see, do you see why programming on a GPU can actually vary a lot in terms of performance? So if you have a code like this, and it turns out that the warp is broken down this way, your throughput is dropping. It can drop quite a bit. So this is one if else. Imagine if you have nested if else, right? If you have nested if else, yeah, it would be fun. This problem is called branch divergence, right? From the earlier example, you ended up not utilizing every execution unit at once, right? This is called branch divergence, and generally, it lowers GPU performance. So if you ended up coding on a GPU in the future, make sure you are aware of these things. There's actually quite a lot of hardware techniques to help fix this. It's still not perfect, but hardware can help. Okay, so it helps a little bit. It helps improving utilization. All right, so are you all with me on branch divergence? Basically, you have if else, and you're not running every single. You're not utilizing all the hardware resources because you have to do branch, right? How about the cache access? So in the CPU, this is okay. So if you are going to enroll in a system skill class, or if you took system skill class before, this is a good recap on what's the benefit of a cache. I have a memory access. I want to access my data. Let's say this is a pointer in C or an array in Java, right? I have load A and load B. Load means that I want to read the data. What's the value of that address? The red means it's a cache hit, cache miss. The green thing, the green box here is a cache hit. So which one will finish first? Load B, right? Because it hit in the cache, I get that right away, essentially. I have my data right away. Then I can keep running. For access A, because I have to get it from the main memory, it takes a longer time, right? So the stall time of A is this long, while the stall time of B is this long, right? So what's the benefit of a cache? Exactly, right? To get your data is going to be much faster. It's going to be much faster. So let's look at cache in GPU, right? GPU also has a cache. But let's say I have a warp where you have a mix of cache hit and misses. What happened here? So let's look at what happened here. The cache hit one will get, okay, I go to the cache, it hits. Yay, I got my data back. Can I resume warp A? So can I continue execution of warp A? Or can I? I still don't have a data for the rest of it, right? So can I go to the next instruction? Yeah, so no, right? No, because you need to everything to finish. You need everything to finish. So you're gonna have to wait until everything got its data, right? So the stall time of warp A is that long, right? So there's another thing that can happen in the GPU cache. So the benefit of having a cache in the GPU is typically sometimes it's not going to be as fast, but it does filter things that you have to access in the DRAM. So basically it lowers the number of requests that have to say, hey, I need my data in DRAM. So in this case, instead of sending 8 things to DRAM, how many are you sending to DRAM? 5, right? Because you have 5 accesses to DRAM. So instead of 8, this thing, the data is in the cache, but the data has to be acquired from DRAM, right? Oh, everyone can hear me, by the way? Okay. Might be your end. Sorry. Basically, the benefit of having a cache in the GPU, one of the key benefit is instead of sending, for example, here 8 different data requests to DRAM, you only send 5. It reduces DRAM bandwidth demand. Basically, now you can service other loads at the same time. DRAM is designed so that it can service multiple DRAM requests at the same time. A cache in the GPU is designed to make sure I can filter out some of those so that I don't overload DRAM. So here's the actual GPU utilization. The restriction is, as I said, you need to make sure every operation that you write in your code, at least the one under the same warp, should obviously have the same instruction. Why? You have a lot of execution units. You have only one decoder. It can't figure out what instruction you are doing in a warp if they're different. Everything needs to look the same. So to get the benefit, parallel threads must be similar. So if you have high parallelisms, but they are not the same instruction, don't run them on a GPU. Otherwise, the GPU would run one thread at a time, and that's going to be really slow, right? So here is a typical. So let's go back one more step. Let's go back one more step. This is a little bit less about parallel programming, and this is more of the okay. Now that I'm convinced my program want to use a GPU, what do I do? This is your computer, right? You have a CPU and you have a GPU. Any questions so far? The left side is your CPU with its own DRAM. The right side is the GPU that you buy and plug in your PCIe. So a typical operation is when you write a CUDA program, the program that would run on the GPU. This is what happened. You will first call a function called CUDA malloc. Anyone here familiar with the malloc function call in C? What does malloc do? Okay. You get my hopes up and say, yeah. It allocates memory, right? Basically, yes, you're correct. It say when I said malloc in C, it means that I want memory so that I can store my data. Basically, it's allocation so that I can store my own data. So CUDA malloc, instead of a typical malloc, it would make sure that you allocate the memory, but on the GPU side. On the GPU side. For example, here you're gonna allocate these blue boxes on the GPU DRAM, right? Then when you are actually say, hey, I have the data that I want to send over to the GPU side, what you would typically do is call CUDA memcopy. memcopy is copy operation from this location to another location. CUDA memcopy would basically copy things from, as I'm going to show here in the animation, the CPU part, transfer it over to the GPU. Any questions so far? Basically, first allocate things on the GPU, then copy things over from the CPU side, and then launch the kernel. Kernel means that it's a compute kernel on the GPU side. Basically, I want to run this function. GPU would then process your data, and then you call CUDA memcopy back to the CPU side. And that's it. That's how you run things on the GPU in a really high level. All right. And this process can be annoying. So NVIDIA also come up with the concept we call unified virtual memory, which basically now you create the illusion that both DRAM, the CPU side, and the GPU is a one single thing. And you can say CUDA malloc manage. The function called CUDA malloc manage would actually perform everything I just said earlier automatically. So CUDA malloc manage would allow you to use your array, and then you say CUDA launch, I run the program on the GPU side. The GPU driver would manage everything. It managed everything. So now it becomes a unified memory, and everything is done automatically. So it moves things around without you having to control that. All right. So to move the data between CPU and GPU, right? Think of it this way, and this is the. So it's what do we call it these days? Master and worker, right? So CPU is a master, and GPU is a worker. The CPU is a host. It sends the data to the GPU. It sends the compute kernel. Basically, the program would get sent by the GPU, the CPU, and it actually tell, okay, start. A GPU would listen to that. Okay, fine, I'll run. It takes the command, execute the code. Oops. It takes the command and execute the code and process it and send it back to the CPU. So remember, when you run things on the GPU, CPU has its own DRAM. GPU also has its own DRAM. This day is GDDR5 or GDDR6. The different technology gives you more bandwidth versus less bandwidth. It's a little bit faster as well. And these DRAM are connected to PCIe, which is on your motherboard, or another thing called NVLink. This is the NV switch available from a lot of NVIDIA products, right? And these are typically a lot slower than the link between your last level cache and DRAM. So moving data around is taking a lot of time. The requirements is if you want to run things on a GPU, the data have to be there first. You need your data there first, right? So to get more performance, what do you want to minimize? You basically want to minimize the data transfer between the CPU and the GPU, right? Because these things take a lot of time, a huge amount of time. So make sure you are aware of that. All right. Then hopefully that's the end of today's lecture. That's the end of today's lecture. Not tomorrow. On Thursday, we're gonna do a little bit of recap on Rust and a little bit of recap on the last assignment, which is out for a while. And then we'll also discuss projects. All right. Next week, is next week the last week of class, by the way? Okay, so next week on Tuesday, I'm gonna show some code running on a GPU, right? The thing here is not all your computer has a GPU to try on. So it's a little bit more limited. I'm gonna just demo the code and take like kind of browse through some of the things that we have, like OpenMP code, GPU CUDA code, and how it looks like. If you're curious, where do you go get more resources? All right. And on Thursday, we'll do a recap of everything we covered so far. Right? Anything today is not going to be on your exam, but I hope you enjoy learning a little bit more about the hardware that I spent my whole PhD on. So my thesis is on how to design a GPU. It specifically on the memory hierarchy and how to make it even faster. So I hope you enjoy the lecture. I hope you learn more things, and I hope you learn what can I gain from running things on a GPU, and what should I avoid being running on the GPU, right? One last thing for the lecture today before we move on to Discord to kind of discuss projects, assignments, homework, or anything is I have a submission guideline, and here's my suggestion. Put it on a GitHub. Anyone here familiar with how to use GitHub? So put it there. Private repository is fine, and make sure you share that with me. Properly write the README properly so that I can understand what you're trying to do. Why GitHub? So this is a good question. You might be wondering, like, why extra work? So first of all, you can use it as your backup, so you don't have a random lost work. And I can also see history of changes in a way that uh can tell, hey, the change is done after the deadline. What's up with this? All right. So basically, this prevents any possibility of like, oh, John, I'm sorry, I lost my code. All right. But the more important side of this is particular last bullet point. So I've seen a lot of you guys that when you apply for a job or like say a master program, in my case, whenever I see new applicants, right? I'll see on the resume and I say, hey, you work on this project, you work on that project. I never see the code. If you put code on GitHub, it allows your potential employers, potential interviewer to check it out, right? These are your hobby. These are your project. You are proud to put it on your resume. So be proud. Put the code on any open source platform that people can check out, right? Uh, this can be done when if you want to put it in a private repo for now and get my feedback and things like that, totally okay. You can decide whether you want to publicly open that when you find jobs, right? But this would allow you to put things on the resume, including the GitHub link. Just a quick thing that I feel like it's useful to know before you hit the job market. All right. And I feel like this is the right time to mention it up because I feel like this class is for like a junior student going to the fourth year, right? So I think it's a perfect time to think about, okay, what do I do? How do I prepare for the job market? Also feel free to kind of chat up with me if you have anything to say about like thing you are interested at or your career, anything. Like, feel free. Just feel free to treat me like one of your one of the people at MUIC. I'm so glad that I get the chance to like teach all of you. Right, it's been fun. It's been really enjoyable. I can't tell you how glad I am. All right. So that's it for today lecture part. I'm gonna wrap up the lecture right now. We'll switch over to Discord. Uh, and yes, you can start your project anytime. You can start like 5 weeks ago too. I mean, you don't have to wait. Basically, just make sure you finish assignment and finish the project. All right. There's no like required start date or anything. And you might have realized that I toned down on the in-class exercise because I want to make sure you start to look at your project. So we're gonna switch over to Discord. Give me maybe it's like 5 minutes to basically I'm gonna go get more coffee. Uh, and then I'll be right back on Discord. All right.